Azad Siddiqui on foliation of asymptotically flat black hole spacetimes, and that was till 2013. So it is interesting to have him as the chair of the session. Quite a lot of the work that we've done together. In July 2021, Tuft and others presented in the Marcel Grossman meeting seemed to have rediscovered what we had found earlier. Work by Roy Kerr and others displayed some confusion that it can remove. So I will be talking about that work. First, foliation, the what, why, and how of it. What it is, well, folia are leaves in Latin, like those of a plant or those of a book. Breaking a solid block into leaves is called foliation. In the context of relativity, generally, breaking a space-time into 1- and 3-dimensional parts, either a sequence of null hypersurfaces with time increasing along the sequence, or a sequence of space-like hypersurfaces with time increasing from one hypersurface to the next. Why should it be done though? What, why, how? So this is the why. Because Einstein had married time to space, and if one goes with the Christian marriage words, that which Einstein has joined together, let no man rend asunder. However, the intuition of most people does not work in the 4-dimensional space-time geometry, but with forces. And even more importantly, quantum field theory requires equal time commutation relations, and we need to be able to unify general relativity with quantum theory, so we need folia. And finally, the how over there. There'd be no unique sequence of time-like hypersurfaces, so that possibility of time-like hypersurfaces is eliminated at the start, and we are left with either null or space-like hypersurfaces for the equal time commutation relation for most purposes, especially for canonical quantization, one actually needs space-like hypersurfaces rather than null. There could be many different ways of space-like slicing of the space-time, and each has its own adherents. We need to keep an agnostic view of it that we don't know and will decide according to how things work out. So there's the canonical formulation, and there's Arnowit Deser Misner had given the formulation of breaking space-time first with these 3 functions, the scalar lapse function n, the shift vector function giving essentially a momentum, a spatial momentum, and the Nij being the spatial 3 metric. So that is the way the classical canonical quantization procedure works. They normally start from here. However, the problem with this is it's not manifestly covariant, which one would want. The Riemann curvature tensor, RABCD, gives the intrinsic curvature of a manifold. If the manifold is broken into a sequence of submanifolds of one lower dimension, there will be a unit normal vector to the subspace at each point. That's written as Ni here. such that their congruences stay the same, so it converges or diverges. This measures the extrinsic curvature tensor, Kij, which is the gradient of Ni. So that will be the measure of how the space is curving as the 3 space. The trace of this tensor, the divergence of the normal, is the mean extrinsic curvature. K is the trace of Kij. So, with the, I think I've gone one forward there. There's the minimal slicing, which is that you choose the space-like hypersurfaces and consequently the time by requiring that the unit time-like vector does not diverge or converge, but it stays parallel. And this is called the minimal slicing, where you keep the extrinsic curvature equal to 0. Dill tried to foliate the Schwarzschild space-time by minimal slicing, but the hypersurfaces got blocked at Rs by 2, so it was not likely to be very useful. The other way is K-slicing that one could go with. You say, let's take the K, the mean extrinsic curvature, to be constant on each hypersurface, and then you increase K from one hypersurface to the next. So it will act like a time. In fact, this was suggested by York and is called the York time. To obtain the foliation in spherically symmetric spacetimes, we choose the radial unit vector T along the hypersurface and the unit vector orthogonal to it as the normal. So T dot T equal to -1. Remember, T is the spatial vector and N is the time-like vector. So N dot N equal to 1. That should be minus N dot N, sorry, and T dot N equal to 0. The Schwarzschild solution that everybody knows, given there, has a metric singularity at R equal to 2gm over C square over C square. Again, the R is unnecessary. If the singularity were due to an infinite curvature, the curvature invariance would diverge there. The first one, the Ricci scalar, of course, is 0 because that's how we get the Schwarzschild solution, is solved for the Einstein to space. You can see it in my book. The second one is given there and goes as 1 over r to the 6th, and that goes infinite at r equal to 0, but has no singularity at 2gm over c square, and so that is the curvature invariant, giving us that you can go through the horizon. So it's a coordinate singularity. You can remove it by changing coordinates. Now the usual space-time diagram for this is time going up and space going perpendicular in that plane as it's shown there. And now matter falls into the nascent black hole as it's forming. The black hole will form once the matter has collapsed within the Schwarzschild radius, 2gm over c square, and then we will denote that by Rs. So that will be the picture. You get the cylinder thereafter going on forever as an eternal black hole. When you change coordinates and go through various steps, finally you get these classical coordinates as Cluscal Sequus coordinates is what I prefer. Cluscal are null coordinates, and these I find easier when you go with time and space. So there's T and R, the usual time and space. And now you can see that there's no singularity at Rs. The space-time diagram for this is called the Cluscal diagram. Now, a problem with that is that you don't really see the space-time as a whole. It's going off all the way to infinity. You never see the end of it. So one would like to bring it to a finite domain, and this was done by Brandon Carter, and these coordinates were provided originally by Carter, used by Roger Penrose fairly heavily. He gave this job to Martin Walker to formalize these diagrams, which were then later called Penrose diagrams by Hawking, and Carter-Penrose diagrams when Penrose pointed out that Carter is the one who had done them first. Unfortunately, he didn't point out that Martin Walker had formulated it finally, and so perhaps it should have been Carter-Penrose-Walker diagrams. Anyhow, there you see the compact version, and I don't know, I can't see it from here quite that well. I hope you can. So I'm going to try to just make the point that there is this is a null infinity future, null past infinity, and that's written as sky minus, sky plus, and here there'll be also null infinities. This is the horizon, and this is the horizon. There's the singularity at r equal to 0 in the past, and this in the future. So with that we go forward. The way for the K slicing then is we've started a given hypersurface, so that means a given K. You start at psi equal to 0, guess an initial psi 0, and solve the equation numerically. That's just a first order differential equation. You solve it numerically, and then in the CP diagram that we had here, you require that this goes to spatial infinity over here, I0. So this is the procedure. If you find that it doesn't go to the right place, the pi 0 place, then you change your psi 0 and go on up and down till it fits the correct place. So this was done in this work of Azad and Amjad Pervez and I that is mentioned there. Now, the limiting hypersurface for k equal to plus or minus infinity are the upper and lower boundaries. That's the r equal to 0, the singularities. So that k will be infinite at the singularity, plus infinite or minus, future or past. And that's the slicing done that we got drawn by hand by me. I couldn't afford to get permissions to take that, so I put it in myself by drawing by hand. I started on foliations because of work that I did with John Wheeler, testing the conjecture of Roger Penrose that in a closed universe, the black hole singularity would form simultaneously with the Big Crunch singularity. For this purpose, we tried different models for a black hole in a closed universe that had various shortcomings for each one. Finally, we tried joining a denser Friedman universe to a rarer one with a Schwarzschild spacetime, joining it together as a suture, and Wheeler called that the Suture Model. So there's the Friedman model metric everybody knows, and there's the three possibilities, the open, flat, and closed, and with the time given parametrically there through eta, you also have then the scale factor given with that time through eta. For the future model, for the Suture model, we need actually the case with k equal to +1 here and here. So this is the Suture model that we'll be working with. However, bear k equal to 0 and -1 in mind, that should be a -1, because they're also relevant for later purposes. Here is the Suture model given at one instant, as it were. You'll see there region A, there's the denser Friedman, and therefore smaller, and the rarer one, therefore larger in here, is B. And this is C in here, the Schwarzschild region. And now you convert it to the Carter-Penrose diagram. So you'll have three parts of it. There'll be this part for the denser, and this is not in there. There's this for the rarer, and this thing isn't in there. And for the Schwarzschild, it'll be this with these two eliminated. So you have to join these three together, and then you have to be able to break this into space-like hypersurfaces so that they all fit together. And you need that this suture disappear at the beginning, and then it'll go to infinity over here because it's hitting the singularity. So we start at the hypersurface in the smaller region, chi-s equal to 0, and you start with some guess eta 0, proceed to evolve along the chosen value of k till we hit the boundary between A and C, and then you proceed in C, and the way you go from one region to the next is that you require that whatever the angle of the hypersurface is on one side, it stays the same the other side, equal and opposite, where you have intersecting lines, you get opposite angles equal. So use that, and so you go forward in the Schwarzschild region in C till you hit the boundary B. So you've started in here, and you go along with the guess value, go on a hypersurface here, keep the angle the same, then you come here, you keep the angle the same, and go through here, and then you come out here, keep the angle the same as you go, and end up somewhere. And then you require that it should end at the right place. So that procedure goes over there. This was what I'd done first before doing the Schwarzschild attempt. So this was done, and the net result was that we got the universe looking something like this. To start with, it's all just one little dot, well actually two dots stuck together, and then this expands out and this expands out, and the join between them goes expanding, the Schwarzschild region. And it goes on, but this is also expanding. So somewhere it will reach a maximum of expansion, and then this will start contracting again, but the length will go on increasing. So it will go this way up to a certain state where then after that this side is contracting, but it will then, because of the length, the size, the average size just goes shooting up and goes off to infinity. So this is the case slicing of the Suture model done. The Reissner-Nordstrom metric is like the Schwarzschild, as everybody knows, with a charge put in there as well. And it has two singularities as coordinate singularities. And then if you have Q equal to M in gravitational units, Q square equal to Gm square, then you will have only one singularity. And if you have Q square greater than Gm square, you'll have no singularity, because this will become imaginary and there's no place where it goes singular. The problem for foliation is that there isn't one coordinate patch, but two. I've mentioned this to Wheeler when I was talking about the Reissner-Nordstrom foliation. He said, "You mean that is a lie, that diagram, this diagram?" It is a lie in the sense that there are two coordinate patches there for each thing. You need to go from here to here in one coordinate patch. But then it can't be extended beyond. From here to here will be another coordinate patch. Or take it the other way, from here to here will be one coordinate patch, and from here to here will be another coordinate patch. So you have to go patching it together and then go forward. This horizon is an event horizon, redshift and infinite time delay, the usual. This is a blue shift horizon, and it has inner structure. This is a trapped surface. This is not. The patches, then, I've just mentioned over there. So, when you do the case slicing, this is the way it goes. This central block is sliced, and you don't enter into this part. So it is non-singular all the way through as you go with the K, going higher and higher and higher. In the limit, it would go to this limit of the horizon, the outer horizon, and that is where you would hit a boundary. It is the Cauchy horizon. Now, instead of asking for zero or constant mean extrinsic curvature, you can ask for zero internal curvature of the space-like hypersurfaces. Now, that's much more difficult to try to actually obtain solutions, because that means you're solving this equation. These are three-dimensional, so Rij equal to 0 in 3 dimensions. That means you have coupled nonlinears, 6 PDEs for 6 functions of 3 variables. And who can solve that? Normally you use mathematics to make difficult physics easier. Surprisingly, here you can use physics to solve this impossible mathematical problem. As Einstein noted, a freely falling observer sees Minkowski space locally about him, so that the freely falling frame, in that the intrinsic curvature is 0. All we need to do then is to determine the free fall geodesics and use those to define the frame. You take them falling freely from infinity, and from there you obtain the hypersurfaces orthogonal to the tangent vector at every point. One can just develop those easily. Though what Wheeler would have called the poor man's way of solving the impossible system of PD is required. And once one obtains the hypersurfaces, one can simply verify that they have 0 intrinsic curvature, which one does. So you've solved the problem of the equations without solving the equations. Writing n for the unit time-like vector along the geodesic, and t for the unit tangent vector to the hypersurface, because t dot n equal to 0 and n dot n equal to 1 equal to minus t dot t, getting rid of the proper time by taking the ratio of the time component of these vectors for the hypersurfaces, we get dt by dr as given over here, with this k being whatever. It's a geodetic parameter, depending on whether you're falling freely or you're thrown in to the black hole. So with that, you have this as a constant of the motion, which you could choose to be 1 for a frame falling freely from infinity. We'd solved with the other values as well, but I'm only showing with k equal to 1. So using these values, we get the hypersurfaces shown here. Then the labeling will be explained later. Notice that the diagram breaks neatly into 2 symmetric parts. There's this one, the right part, and there's this one, the left part. We will only deal with the right part as yet. That. The upper right part of the CP diagram, you can see that the time is going up from here to here as you go. The earlier hypersurface, the later one, later, say later. So these are spaces of simultaneity, so the time is going from here to here, from D to C. So let me make the point, this will be I plus, then this will be I minus. When we were doing the K slicing, this was I plus, but now this will be I minus, and that will be totally different. So this I'll be talking about later in the implications. The expression for dr by dt for the hypersurface for Reissner-Nordstrom is much more complicated, but in principle goes in the same sort of way, and it breaks this way so that you have this diagram only to look at. That's the equivalent of the right side. But now, of course, this goes infinitely, so above this there'll be another block that goes like that. And then that one, this will go straight up like this here, this thing coming over here. Just this one above this. So you'll go straight up like that, go over there, and then that way. Now that would be the next block, and then you'd go on that way, and that's what would produce this, if I get to the, that's what would produce that. So you'd have this as one block, this is the other block, that's another block, and so on. Go on up, joining them that way. So let me get back, and that's what we've got. As the model for the Suture model evolves beyond a critical extent, the suture stretches into a corridor, and if I had an antipodally placed black hole, not just one black hole in the Suture model, but two, one placed either side, there will be then essentially the two corridors pushing out either side. So there, if you will go still further, this will then, with many black holes, it will become like a spiky ball. And this is for a static black hole, but then if there was shear in the model, so the black holes are moving in the universe. So in that case, you would then develop the generic approach to the cosmological singularity of Belinsky, Khalatnikov, and Lifshitz. With more black holes, it would not be just a few corridors, it would become a mess of tangled corridors, ending up like tangled strings tied in one tiny knot at the center and then flapping around all over elsewhere. So that is the picture. The BKL oscillations were worked out for homogeneous cosmologies. For non-homogeneous cosmologies, the model implies an ever-lengthening tangle of waving strings. As the corridors become longer, they become narrower. If one uses the foliation for a flat or open universe, they must become so narrow as to violate quantum uncertainty and may then bounce back time symmetrically. In that case, it must become a white hole. So if it becomes a white hole, there's no information loss. So no information loss paradox, and it will just take care of it automatically, because either if it is a closed model, then the information collects back together at the end, or if it's an open or flat model, then it comes out all over again, and so there's nothing, no information loss involved. I'd explained this point to Susskind, and he felt this would be revived and published properly later. With Wheeler, I found that for K-slicing the Suture model, as one approaches the future singularity, its proper length seems to go to infinity. However, we had no analytic proof, only the observation that the number of steps goes on increasing as you go further and further. So on this, Wheeler had said, so near, but analytically so far, so analytically far, as he put it. I did this work with my student Qadir and we proved that this was there. And it went with k to the 1/3 as the length and 1 over k for the volume in 3 dimensions. Asghar and I then went on to look at this for the Schwarzschild, and we found that there was a log natural k that had to be included also. We then extended it to spherically symmetric n dimensions, and when you do that, you find that the volume goes in a different way. Length is the same, obviously, but the volume goes as 1 minus 2n over 3. And so for a three-dimensional black hole, which is referred to heavily in the literature, you have k to the 1/3 log natural k for the volume. So instead of collapsing, it explodes. It's not a black hole. All the superstringers and Dane theorists can say what they like. It isn't a black hole because it's got an infinite volume. I explained this to Amir Iqbal. He said, I'll look at it and get back to you. And that's the last time he got back to me on it. So there's no answer to that point up to date. For the Schwarzschild space-time, it's worth considering the limits of K-slicing and flat foliation. In the former, K goes to plus minus infinity, and the hypersurface is as given there. As such, the upper, lower left, or either upper or lower left or right corners are I plus or I minus. And the arrow of time goes up in one direction and down in the other, so they'll go opposite sides. As such, an angled arrow, upward arrow, is what you get falling in from one side. From the other side, what it will look like will be a white hole. I asked Penrose and Wheeler about this ambiguity. I got no answer from them. I discussed this in the free fall frame. It corresponds to a special Fermi-Walker frame and gives the Newtonian force of gravity for the Schwarzschild metric. And the idea had been that this would be the frame relevant for quantum theory. This was being pursued by Amjad Pervez and I, but through the problems of that, finally things got done better with Asghar. We were following the following procedure, and we found that the problems of quantum theory of ambiguity was resolved because of the horizon disappearing. That point had been made by us, and it was noted 29 years later by Tuft in his plenary talk. For the Reissner-Nordstrom space-time, there appears to be a big difference between the Schwarzschild and Reissner-Nordstrom space-times. Because whatever small charge you may put in, the CP diagram, instead of being compact, becomes non-compact. It goes off to infinity there. So for the K-slicing, it's only the central block that remains, and the singularity gets smeared out onto the outer horizon, as I mentioned earlier. The same would apply for the Kerr metric. In his plenary talk, Roy Kerr argued that there's no singularity for two masses orbiting about each other based on the slow approximation. That's an approximation. So it doesn't actually prove anything exact, so his claim wasn't really meaningful. But in any case, there is an inner horizon, and on the generic behavior expected is that it is a Cauchy horizon on which the singularity appears smeared out from the K-slicing picture. This confusion also appears in the talk of Hua, Yuan K. Hua, in which he argued that there is no singularity because he used the space-time picture instead of the CP diagram. The interesting feature of the Rn black hole is that there's a repulsive force on neutral matter. The force is defined on the flat space-like hypersurfaces of our foliation. The attraction remains greater than the repulsion outside the horizon, but is less sufficiently close to the singularity, and so the Judy-6 bounce and go out to a new universe, even for an extreme Reissner-Nordstrom black hole. And that is shown over there. I can't see it well enough, but I hope you can. So you notice that there is this boundary barrier that you have outside R equal to 0, and the space-like hypersurfaces then go from one to the next, and the orientation runs backwards. So the CP diagram for the naked Reissner-Nordstrom singularity looks just like for the Minkowski metric, except that it has a singularity at R equal to 0. There's a boundary at the classical electromagnetic radius at which time-like Judy-6 bounds and get to time-like infinity. null geodesics do not, but the back reaction of the space-time gives them an effective mass resulting in a bounce. So we get censorship without censorship. The CP diagrams for particles falling freely from infinity and thrown in from infinity is given there. The boundary is maximum for free fall. When it Hooft made his point regarding this thing, Abba Ashtaker had asked what would happen for the Reissner-Nordstrom, so that there'd be no Hawking radiation in the case of Schwarzschild. How about Reissner-Nordstrom? And the answer is that the same argument holds, and this answer was given long ago, and I'd given it more recently, repeated it again. There would be no Hawking radiation there either. So this is a good time to pursue foliation further. Thank you.
Well, a nice talk, and it is right on dot. We have time, 2-3 minutes for some short question, if there is any.
In a slide, I see the word Foliation. So,
नहीं वो तो आवाज़ वहाँ निकल गई है मगर मेरे सुनने के अपने मसाइल.
what is the meaning of the Billy shift? If we talk about the red shift, then we say some change in the wavelength. But Billy shift, what is the meaning of the Billy shift?
What does the mean?
Okay. The difference, what is the difference between blue shift and red shift?
Oh, when you have light coming from one place going away, then you get it redshifted from inside a gravitational well. Then the frequency reduces and it is then redshifted, the wavelength increases. Now, if you've got light coming from outside into a gravitational well, then the frequency will increase. The wavelength will decrease. That will be a blue shift. So when the light is coming from the horizon going to infinity, it gets redshifted, infinite redshift. When you go from the light coming from infinity to the inner horizon, after having passed through the outer horizon, it goes into the inner horizon, it becomes infinitely blue shifted. That's an infinite blue shift horizon.
Thank you.
Any other question? Any other question? If not, let's thank Professor Asghar once again.